the low voltage case, it results to what? The high current, and high current may leads to thermal breakdown. And we have seen, I told you already that this kind of situation, that low voltage problem may occur during the summer holidays or summer period or summer duration. And here you may get in winter. During winter, you are going to get what? The high voltage problems. I explained you very clearly. And the high current may lead to thermal breakdown, and high voltage may lead to what? Insulation breakdown. So I give you time now, and just keep noting down all these things quickly. And I will also give you some points, okay? Explain you some points. I give you the notes, okay? First, you please quickly note down all these things. You just go in this way. That's it. So these are the two examples you are seeing. Here you got a low voltage problem. Here you got high voltage problem. This is very important with respect to the interview. Yeah, people may ask you simple questions in the interview. Okay, they may ask you that how the high voltage problem arises, how the low voltage problem arises, and what could be the consequence. The consequence is very important here. What will happen when high voltage problem occurs? What will happen when the low voltage problem occurs? Okay, just note down these things, and then after this, you can note down certain points. First, you note down this quickly: ideal voltage source, practical voltage source. That active convention, passive convention, I will also explain you. Don't worry about that. I will also dictate certain points. So now you write down, note the first point. High current may lead to thermal breakdown. Thermal breakdown. High voltage may lead to high current may lead to thermal breakdown, and high voltage may lead to insulation breakdown. These are the two important points you need to note down. Very, very important points, interview point of view. Third point also you can note down: low voltage problems. Low voltage problems occur during summer. Okay, during summer. High voltage problems occur during winter. Hope you understand this. Okay. Low voltage problems occur during summer, and high voltage problem occur during winter. These are the very, very important points in the interview point of view. I'm not deleting that matter, okay? I'm just deleting this part. Don't worry. Okay. Third one. Ideal current source. Ideal current source. What is an ideal current source? It also supplies finite power for infinite time. But what is the internal resistance of an ideal current source? It is infinity. Usually you represent the current source like this, capital I. Practical current source. Practical current source. The internal resistance value is very larger value. It should be as larger as possible, larger value. Okay. And the representation of the practical current source is that I comma capital R. What is this capital R? It is the internal resistance, which is always a larger value. But I told you already, in the network analysis, we have an important assumption that all elements are ideal. So we need to convert the practical elements into ideal. Mathematical models are available. It is usually, okay, represented with a parallel resistor model. I. So what is this dotted? This is ideal. What is this total? This is practical. You understand? Okay. Ideal and practical sources. So what is a practical current source now? Practical current source is nothing but an ideal current source with a parallel resistor. We have seen practical voltage source. Practical voltage source is an ideal voltage source with a series resistor. Practical current source is an ideal current source with a parallel resistor. So this is how you can go. Okay. So therefore, you can also write down note. Practical voltage source is nothing but, please note down, is nothing but ideal voltage source with a series resistor. Please note down all these things, all of you, quickly. Practical current source is nothing but an ideal current source with a parallel resistor. Okay. Practical voltage source is nothing but ideal voltage source with a series resistor. Practical current source is nothing but an ideal current source with a parallel resistor. Please note down all these points carefully. All are very, very important here. Note down all those things, all of you. Some points let us write down here. Very, very important points. Okay. Let us take now Vs and Rs, and load is connected here. Let us see the load characteristics. The load is RL actually here, plus minus VL, and this is IL. Now let us draw the characteristics VL versus IL. Okay. Now let us apply KVL in this. KVL, to apply KVL, the algebraic sum of the voltage must be 0. And the voltage is available, but what is the voltage here? IL into RS. But what are the polarities? Direction is like this, right? The direction will decide the polarities. This is the direction, therefore these are the polarities. Therefore RS into what? IL. Now let us write that VL is equal to, even you can use the touching concept. Okay? VL is equal to touching negative, touching positive. Therefore plus VS minus RS into IL. So from this we understand if IL increases, that means load current increases, which happens during the summer. Just now we have seen. During summer, what happens? The load increases, the load current increases. Then the drop across this one increases. Then VL decreases because VS and RS are constant values. Yes or no? Okay. Now you take an ideal condition. What will happen? RS is 0. Therefore, what do you get? VL is equal to VS. That means the load voltage is same as source voltage irrespective of the load. Irrespective of the load voltage is same as the source voltage. Because in ideal condition, RS value is 0. But it never happens. It's an ideal case, not a practical case. Okay. So if you draw the characteristics, that load voltage versus load current, if you draw the characteristics, let's see what will happen, how it looks like. Okay. You're drawing the characteristics. This is IL and this is what? VL. This is constant. Ideal condition. But what is practical? Drooping characteristics. The voltage decreases with respect to the current, we have seen already. But ideal condition, it is constant. Why this gap is coming? This is due to drop across, okay, RS. This is practical. I'm just writing practical, this is ideal. Understand? Let us also take the second one. I give you time. First look at this. Okay. Current source. What is the current source? How it looks like? A practical current source is nothing but what? An ideal current source with a parallel resistor. Let us take the load now. What is the load connected across here? RL. What is the current flowing here? IL. What is the voltage across here? VL. Okay. Now let us try to get the relation between IL, VL, IS and RS. For that, let us take KCL, Kirchhoff's current law at this node. If you apply Kirchhoff's current law at this node, what will happen? When you apply KVL in this loop, okay, you got this right. When you apply Kirchhoff's current law at this node, you get IL, that is a leaving current. That is a leaving current. This is an entering current. But what is the current flowing here? Then for that you require voltage. What is the voltage actually appearing across the same voltage? So this is also VL. And you know the polarities. Based on the polarities, you can indicate the direction of current. And it should be VL by RS. Now let us look at this. IL is leaving. VL by RS is also leaving. Okay. VL by RS is also leaving, but IS is entering, and finally IL can be written as IS minus VL by, okay, RS. This is what actually the relation. From this, you understand that because IS and RS are constant, okay, when VL is increasing, now let me take VL on x-axis because it is a current source we have taken. VL is increasing, then IL is decreasing. What happens in ideal case? In ideal condition, you know that RS is infinity. What is the internal resistance of an ideal current source? It is infinity, we have already discussed. Therefore, From this, we understand IL is equal to, what is it? IS. That means load current is same as source current irrespective of the loading condition. Okay. Now, if you draw the characteristics for this particular case, the VL is on x-axis and IL is on y-axis. You get now the constant. This is ideal condition. Just now we have seen ideal, that is IS. Okay. But you know that when VL is increasing, then IL is what decreasing here. Therefore, you get a drooping characteristics. This is due to current in RS. Okay. This is due to voltage drop across RS. Okay. So, just please note down, this is a practical case. I'll give you time, note down, I'll give you 2 minutes time. All of you please speed up. Hope I think you have written this part clearly. Okay. This is second, right? Now third one. All of you continue. Okay, let's take the continuation part. Third one. Let's take the continuation part. Third one. Write down that statement clearly. Voltage source must not be short circuited. Tell me what will happen if the voltage source is short circuited. You know that voltage source is offering a very low internal resistance. I is equal to V by R. When it is short circuited, I is equal to V by R value is very small, denominator. Then high current passes. High current may lead to thermal breakdown. Just now we have discussed that point a little while ago. Yes or no? Therefore, write on the point here, voltage source must not be short circuited. If it is short circuited, then it may lead to damage of the source. It may lead to damage of the source due to high current. Yes or no? Due to high current. High current, what will happen? It leads to, actually, high current may cause what? Thermal breakdown. That's why better you write in bracket thermal breakdown. That's it. Okay. So let us see some interesting points which we should really understand before we get into the problems, how to solve the networks. One should really aware of all these points. May be important in the interview point of view, may be important in the analysis of certain complex networks. Okay. Anyway, in the gate point of view, we are going to discuss several examples, several problems. Do not worry. But let us try to first focus on the concepts here. Okay. Look at this, all of you. First, let me take an ideal case. Sorry, practical case. Okay. First, let me take practical case. Then I'll go with ideal case. Okay. It will give you more clarity if I go with practical case first. So, what is the practical case? Assume that this is 1 volt. Usually this value is very smaller. Let us say it is as smaller as 0.01 ohm. What is the statement? Voltage source must not be short circuited. Let us see what will happen if it is short circuited. This is short circuit. You know that this entire path is having only one resistor. Therefore, what is the current actually here? I is equal to 1 by 0.01. That is 100 amperes. 100 amperes is not a small current, Nana. Yes or no? 100 amperes is not a small current. 100 amperes is flowing through this particular source, then definitely it may lead to damage of the source. Okay. If you take ideal case, I'm just elaborating. Ideal case, then what is the current actually here? Infinite current. Yes or no? Because ideal condition, what is the denominator? 0. If this infinite current flows, if infinite current flows in 0 time, suddenly, or in 0 time, what do you call it generally? Infinite magnitude with 0 duration, what do you call it? Infinite magnitude in 0 time, what is that signal you call it? You call it impulse, and you call it ideal impulse. Yes or no? So you call it ideal impulse. Ideal impulse current. Yes or no? Okay. So this is what the scenario now. See, practical case, if it is short circuited, 100 amperes current is flowing, taking 1 volt and 0.01 ohm. Okay. If you take ideal condition, the current is infinite. If you really make this current happen in the loop suddenly in 0 time, then what will happen? Suppose if infinite current flows suddenly, okay, then you call it what? Then you call it what? Ideal impulse. Yes or no? So this is a very important point which we are going to use in transient analysis, inductors, capacitors, behavior, characteristics. Okay, but at basic stage itself, we should have an idea what is an impulse current. Let us also take an ideal case now. Already we understood ideal case here, but still I'm just drawing it. Look at this. It's a very interesting point to be observed. There are so many things which can be easily analyzed if you understand this point. It must not be shorted, but I am short circuiting. Let us see what will happen. What is this value? 1 volt. What is the current that we have observed just now when the denominator is 0? How much it is? Infinite current. Infinite current is flowing in the loop. But one more thing which is very important to be observed at this stage is that when you apply Kirchhoff's voltage law in this particular loop, Kirchhoff's voltage law states that the algebraic sum of the voltage in the closed loop must be 0. But do you have that algebraic sum 0 in this particular loop? +1, there is no -1 to get 0. So what's happening here? Kirchhoff's voltage law is getting violated. Hope you understand the point. Understood? Infinite current flows, Kirchhoff's voltage law gets violated. Both the things happen same time. You cannot say, sir, there is a KVL violation, but I am getting a finite current. It's not possible at all. You understand? You cannot say, sir, infinite current is flowing, but KVL is satisfying. No, it's not possible. Definitely, wherever KVL is not satisfied, there infinite current flows. Wherever infinite current flows, it implies that KVL got violated. This is a very, very important observation. That is why I told you in one of my previous sessions. Okay, if you have 100 loops, 99 loops, KVL satisfied, but one loop KVL is not satisfied. I told you that circuit is an invalid circuit. Why it is called invalid circuit? Because if you connect like that, it leads to infinite current. Wherever KVL is violated, it leads to infinite current and it will damage that entire circuit. Therefore, that combination is called invalid. It's very, very important observation, and based on this, there are beautiful problems in the transient analysis. Okay, I put a title called, special problems in transient analysis. Based on this point only, I'm going to discuss. This is a basic point, nothing new in this. This is a basic point, but observation is very, very important here. Okay, so put a note and write down. First you note this. Okay, I'll give you some time, please. At a faster rate, you can note down. Okay, please note down and write down. I'm writing here. First you note down, then you proceed with me. Wherever KVL is not satisfied, there it results infinite current. Okay, and wherever infinite current flows, it implies that KVL got violated. Okay, therefore the circuit is said to be invalid. Therefore, the circuit is said to be invalid. Wherever KVL is not satisfied, there it results infinite current. Of course, vice versa, it is possible. And wherever infinite current flows, it implies that KVL got violated. Therefore, the circuit is said to be invalid. That circuit where the KVL got violated is an invalid circuit. This point we have already written in one of the previous sessions. Okay. So I think you have written all these things right. Now this fourth point, which is very, very important, similar lines. I think now you got an idea. Okay. After looking at all these things, now I think you got an idea. What is that? Current source, right? Current source must not be, what is that? Open circuited. If it is open circuited, please write down. After writing down that, please come back here. It may lead to damage of the source due to, what is that? Is it high current or high voltage? High current or high voltage? High voltage. It is high voltage. And high voltage is, okay, high voltage may lead to what? Insulation breakdown. Insulation breakdown. So I think you have noted down these things, right? So please quickly move on to that point as well as this point, fourth point. Please note down a little faster. I think you have noted down this, right? So let us also understand what will happen when the current source is open circuited. That's very, very important. Actually, most of the people are not aware. They may tell the statement that must not be opened, but when you're asked to prove it, then again, most of the people get stuck. Look at this. It's very important in the interview point of view. Now, let me take first practical case, okay? Practical case. What is the practical current source? How it looks like? Tell me. Okay. Actually, it must not be open. But let us see what will happen if it is an open circuit. Open circuit, right? Let's see what will happen. Assume that this is 1 ampere. Just for easy understanding sake, I am taking 1 ampere. And assume that this is as larger as 1000 ohm. Okay, as larger as 1000 ohm. Generally, what is the resistance offered by the current source? That means the internal resistance offered by the practical current source. How much it is going to be? It should be a larger value. Yes or no? Ideal case it is infinity, but practical case it is a larger value. Now, what is the open circuit? When you have an open circuit, this entire current, it definitely does not flow through this particular path, and entire current passes through 1000 ohm. Then what is the voltage across it? The voltage across this is 1000 ohm into what? 1 ampere. Therefore, how much it is? 1000 volts. Remember, 1000 volts is not a small value. Yes or no? If you replace this 1 ampere by 10 ampere, then this becomes what? 10,000 volts. If you replace this 1000 ohm by 10,000 ohm, it becomes 10 amperes into 10,000, it becomes, 10 power 5 volts. It's not a simple thing. And there is a possibility that the source may get damaged because of the high voltage. High voltage may lead to insulation breakdown. It's too dangerous. Okay. Now, look at this. Ideal condition if you take. Just now we have seen in the case of practical voltage source, right? So ideal case, what will happen ideal case? What will happen ideal case? Let us move this particular value towards the ideal. 10,000. 1000 is replaced by 10,000. This voltage will become 10,000 volts. This resistor is replaced by 10 power 5. Then the voltage will become 10 power 5. This resistor is moving towards the infinity. Then the voltage will also move towards the infinity. This is how you need to explain. This is how you need to explain. Look at this, all of you. When this is 1000 ohm, 1000 into 1, you have 1000 volts. Suppose let us move this 1000 ohm towards the infinity. Why I am moving towards the infinity? Because I am trying to get an ideal case. What is an ideal case? This resistance value must be infinity. When this 1000 ohm is moving towards infinity, then this 1000 volts is also moving towards the infinity. Therefore, ideal case, the voltage will become how much? Infinite voltage. I think all of you are understanding this point. Now, if infinite voltage appears, this is an additional information, okay? Voltage appears in 0 time or suddenly, then you call it ideal. Infinite voltage in 0 time, ideal impulse voltage. You call it what? Ideal impulse voltage. Now let us see an ideal case also, which is very interesting case. Ideal case. Okay, I think all of you understand why the current source must not be open. What's happening here when it is open? It leads to the high voltage. It leads to the high voltage. If you go to the ideal condition, infinite voltage is appearing here. Infinite voltage means on this part, the source will get damaged or the circuit will get damaged. Look at this ideal case. In ideal condition, look at this. What is the current actually here? 1 ampere. 1 ampere. What is this resistance? Tell me. Infinite ohm. What is the voltage that you have already proven here? Okay. Infinite volts. Yes or no? Infinite voltage is appearing across what? These two terminals. We have just now proven, okay, here. Now look at this. Since it is open circuited already here, since it is already open circuited, this entire current, look at this, is entering into what? This particular node. But if you look at the Kirchhoff's current law at this node, 1 ampere is entering, and this is also open circuit, this is also open circuit, and no ampere is leaving. no ampere is leaving. Therefore, what is happening here? The KCL gets violated. The KCL gets violated. You understand all of you, okay? Infinite voltage is appearing and KCL gets violated. Both the things happen same time. Okay, you got KCL got satisfied, but infinite voltage is appearing, not possible. Okay, KCL is getting violated, but finite voltage is appearing, not possible. Definitely both the things will happen same time. Wherever KCL is not satisfied, there it results in infinite voltage, no doubt in that. Wherever infinite voltage appears, it implies that KCL got violated at one of the nodes in the given network. Understand all of you? Okay. Therefore, I can write the points here. Wherever KCL is not satisfied, let me write it now, not satisfied. There it results, what is this? Infinite voltage. There it results infinite voltage. And wherever infinite voltage appears, okay, wherever infinite voltage appears, please note down, all of you, please note down step by step. These are all very, very important points. Wherever infinite voltage appears, it implies that KCL got violated. Therefore, the circuit is said to be invalid. You understand all of you? That is why I give a statement that when you have 100 nodes, 99 nodes are satisfying KCL, but one node, the KCL is not satisfied. Okay? Therefore, the circuit is called invalid. Why it is invalid? If you connect the circuit, it leads to infinite voltage and it will definitely leads to the blast of that circuit. Okay? That's why you never go for that combination. You have to see that all nodes are satisfying the Kirchhoff's current law. Please note down that quickly. I think you have noted down. So that is why voltage source must not be short circuited. Current source must not be open circuited. You should explain that why they must not be shorted, must not be opened in this manner. Okay, so be careful. And now coming to, there was some question, okay, in one of the interviews, one of my students got faced and he just shared with me, okay, which of the following circuits are valid? Which is or are valid? First one, he gave this. All are ideal elements, but DC. So which is valid, which is not valid? Note down this, all of you. This question was asked in one of the interviews, one of my students actually, who faced the interview, then he just shared with me. So this is what actually the question given me. Okay, of course he could answer certain things, but he could not answer certain things here. I'll tell you how to answer it. It's a very easy question. Look at this, all of you. There is a DC source, all are DC sources, and all are ideal elements here. Now, which of them is or are valid? Okay, which of them is or are valid? So look at this. Under DC conditions, the inductor behaves like what? Under DC, inductor behaves like what? Short circuit. Capacitor behaves like what? Open circuit. Yes or no? Inductor behaves like what? Short circuit. Capacitor behaves like what? Open circuit. Now, if it is shorted, then voltage source is getting short circuited. Voltage source must not be short circuited. Just now we have lent it. Yes or no? Okay. Therefore, this particular one is not valid. Okay. Now here the capacitor is acting like what? Open. Yes, voltage source can be open or may be open. There is no problem. Voltage source must not be shorted, but can be open. That's not a problem. Similarly, current source now. Now this is a short circuit. Current source is short circuit. Current source can be short circuited. The current source must not be open circuited. Yes or no? Therefore, it is valid. But current source is getting opened here. It cannot be. It is not a valid one. Yes or no, all of you? Okay. So this is how you need to answer. Okay. This is a very important question, but simple question. But you need to explain that why I cannot connect. Okay. The problem comes, why. Then why means just now I have explained to you. Ideal case, practical case, KCL gets violated, KVL gets violated here KCL gets violated. All those things you are supposed to demonstrate clearly. Okay, that definitely the interviewer will get a positive impression once you try to answer in this manner. Okay, so very important. Note down quickly. Then we switch over to another classification. Before we go with another classification, the first one is passive convention. According to this, the current enters into positive terminal of a passive element so that it absorbs power. Okay, something like this. This is, let us say, Z. There's a passive element, definitely passive. So if you have the terminals like this, then the direction is something like this. If you know the polarities, you know the direction. If you know the direction, you know the polarities here. Understand? Okay, it's very important. Next one, second one is active convention. What is active convention? What is active convention? This is for active element, no. Okay, whereas this is for passive element. Active convention says that, look at this. Example, this is V. Okay, the current delivers, let me write it clearly. The current delivers from positive terminal of, delivers or leaves positive terminal of an active element so that it supplies power. Look at this. This is I. And in case of current source also, you have, this is I plus minus V. Okay. Here also the current is leaving from positive terminal. Okay. So this is what active convention and passive convention. Remember, provided here V is positive, then I is positive. Here also I is positive, then V is positive, that current I is leaving from positive. The current I is also leaving from positive. It looks like entering into positive. Please take it as I is leaving from positive. So this is what I can stop the session here, and I can continue the next part in the next session. Okay, which is very interesting discussion is carried out in the next sessions also. These are all the fundamentals which are very, very important. Okay, I stop here.